Last one, we have mentioned about the moment distribution, and then I have just illustrated the way how to perform the moment distribution method, and then to analyze for the continuous beam. And the last one, we have mentioned about an example here, and then to show you how to deal with an example if we have a so-called the cantilever or the hanger beam. And then using the same way, actually you can see here, we can solve for the answer for hanger beam. And then for this one, actually it is quite straightforward. And then afterward, you find the member ends moment. Then using the equilibrium, you can find for the shear force. And then you can draw the shear force and then the bending moment diagram accordingly. And then as we mentioned just in the tutorial, if you have the end support as a roller support or the pin support, instead of using 4E alpha L, you will use 3E alpha L to simplify your calculation. Then you can find the bending moment using another type that not both sides are the fixed, while one is fixed and then the other one is the roller support or the pin support. Then use that one to simplify your calculations. For other cases, actually you can ignore them because actually it is just for your reference. Say for example, if you have a beam like this, actually we have illustrated a similar one in our tutorial. Then actually you remember that you will choose the bending moment using this type because it is WL squared over 8. And then don't use this one because this is both sides are the fixed end, okay? You should use this one because this the end support is the roller support. Then by using this one, actually you can simplify your calculations and then you can determine your member ends moment immediately. And then you can use the so-called equilibrium equations to find the shear force at the member ends, and then also find the support reactions. And then finally, you can plot your shear force and then your bending moment diagram. So this one actually we have already illustrated in the tutorial. And actually the moment distribution method can also be applied to frames. And then this is actually one with the no sideway for the frame. Well, actually, we just use the same procedure, and then they can also be applied to the frame. So, for example, you can see that we have a frame here, which is actually have no sideway reactions. That means when you apply the load, as actually there's a constraint at the location E. So your frame will not deform literally. So it is actually a frame with no sideway. So for this example, we want to determine the internal moments at the joints of the frame as shown. There's a pin at the E and the D, and then it's a fixed support at the A. So right here, we will use similar way to find for the moment. So for here, actually, you have a fixed end moment at the location B, and then you have fixed end moment at the location C. You will check the fixed end moment accordingly, and then find it by WL squared over 12. And then you can see that you will distribute the moment among the member AB, BC, CD, and then the CE. Then you will use the stiffness factor KAB, KBC, KCD, and KCE as shown. Now, because A is a fixed support, so you will use 4EI over 5. And then for BC, you can see that actually this is just similar to what we have done before for internal members. We also will use both sides of fixed ends. So it is 4EI over L. And both the support D and the support E are actually the pin support. So we will use 3EI over L. So you can see that we use 3EI over L here, and then we use 3EI over L right here. Because these are pin support, and then these are also pin support. Then for the DFAB, actually it is equal to 0 because it is the fixed support here. So all the moment will be absorbed by the fixed support. While for the BA, then you can use the so-called stiffness factor of BA here, and then over the sum of the stiffness. So you use 4EI over 5 divided by 4EI over 5 plus 4EI over 6. So these two is the sum. And then you will put this one as the denominator. I mean numerator. Then after finding DFBA, then you can find for the values of BC, you just have 1 minus this value because this value belongs to this member. And then for the other members, actually you just use 1 and then minus the diffraction, the distribution factor. Then you can find the value 0.455. Similarly, you can find DFCB and then you can find DFCD. Then you can see that because this join, there are 3 members joining. So actually you will have, when there's a moment applied at the joint C, then you will have a portion distribute to the CB, distribute to the CD, and then distribute to CE. So you have the distribution factor to CB, CD, and the CE, okay? So you can see that 33% will be distributed to CB, 29.8% will be distributed to the CD, and then 37.2% will be distributed to CE. And then you can see that basically just the span BC will be fixed end moment. So don't worry about that. This question mark is actually just means kilonewton meter. Okay. So you have WL square over 12 on the left hand side for the BC, and then for CB again it is WL square over 12. So similarly, we will write down a table like this. So first of all, you would write down join A, B, C, D, and E. And then of course you will have the member A, B, and then you have BA, and then the BC. And then the C, you will have CB, CD, and CE. For the distribution factor, well, actually, as I mentioned, at the location A, actually it's the fixed end. So actually, all the moment will be absorbed by the fixed end. At the location B, then the moment will be distributed to the side BA and then the BC. And then at the joint C, it will be distributed to 3 members. We will distribute to CB, CD, and then the CE. So for this one, you have 3 distribution factor here. While D and E is actually a pin support, so basically no moment will be distributed or carry over to the pin support. So first of all, you can see that at the BC, you will have 2 fixed end moment. And then within this joint, actually, they will be in equilibrium. For the joint B, actually 135 negative is the moment. And then you need to apply 135 to the joint B in order to balance this negative 135. And then 54.5 will be goes to the left hand side, while 45.5% will go to the right hand side. So you use 135 times 0.545, then it is equal to 73.6. And then the remaining is 61.4. And then for the joint C as well, you have 135 here, and then it will be distributed to the 3 members. So in order to balance the moment, then you have to apply negative 135 to the joint C. And then you can see that 33% will go to the first member, and then 0.298 will go to the second member, and then the last one will be 50.2. After the distribution, you need to carry over to the other side. No need to carry over to D and the E, because actually they are the pin support, so you don't need to carry over to the other side. So you can see that there's nothing here because actually they are pin support. Then you will repeat the process until the values are very small. Then you will add all of them together, and then you can find that the moment is equal to 44.5 at the AB, and then BA is equal to 89.1, and so on. So accordingly, you can draw the bending moment diagram for the frame structures. So basically, this is for the frame. And actually, the method can also be applied to a frame structure with sideway. Now, first of all, I would like to mention that for the frame with sideway, it is not in our scope of study, basically, because it is a bit tedious for you to find the answer. So here I will just demonstrate to you how to find the solution, but I won't put it in the examination because it is too tedious for you. So, but at least you need to know the way how to solve for the answer, okay? Now you can see that for the frame with sideway, that means when you apply the load to the frame, then it will deform laterally, that means horizontally in this case. So you can see that because you apply the load in an unsymmetric condition, so the frame will actually deform in the horizontal direction. And then that means it will have the sideway. That means it will deform laterally of the frame. And then for this one, actually, how we can analyze our structures? Well, actually, we can use a method of superposition. And you can see that for the first frame, in order to restrain the movement of the frame, we will apply a support right there and make the frame to be no sideway, and then we apply the load. But you can see that the frame actually is not restrained laterally. Okay, so well, actually, in order to show the original case, we need to apply R to the right-hand side in order to eliminate the effect. So to find all the member ends moment, we need to add case 1 and then case 2 together. Okay, then I can find the moment in our frame. Okay. So for here, I have an example, and then to illustrate the idea to you. So we want to determine the moments at each joint of the frame shown here. And then for here, EI is a constant. And then for here, we assume that there is a support at the location C, which restrain the movement of the frame. So for this one, again, we will find the fixed end moment at the section BC right here. We can check it from the table as shown before. And then we will carry the carry out the so-called the moment distribution as before. So you can see that we have our fixed end moment, and then we will distribute our moment among the joint, and then carry over to the other side, and then we will distribute our moment among the members and carry over, just like what we have done before. So this one is actually the very similar to our previous process. And then afterward, you can see that you have the member ends moment here. And then you can determine the shear force according to the equilibrium equations. And then you can see that there's a 1.73 kN pointing to the right-hand side, while there's a 0.81 pointing to the left. So if you are taking a look to the summation of fx is equal to 0, then you have 1.73 pointing to the right, and then you have 0.81 pointing to the left. That means actually there's a force, the force difference of 1.73 minus 0.81. So the force is actually equal to 0.92. That means actually there will be a reaction force which is equal to 0.92 acting as a support. in order to balance the horizontal force at the member ends. Otherwise, the summation Fx will not be equal to 0. Okay. So from here, we can find that actually the resisting force at the joint C is equal to 0.92. Okay. Then afterward, we should apply the force at the corner C, of course, in the reverse direction, and then find the member ends moment. And then afterward, we will add the two moments together to find for the answer. Now to do that, actually, first of all, we assume that there will be a fixed, we assume that there will be a horizontal deflections at the joint B and the C. And then we assume that it will cause a fixed end moment at the members AB and then the CD. So you can see that we assume that there's a delta dash implied at the joint B and the C, which will create a moment, negative 100 kNm at the member ends of AB and CD. And then by assuming that, actually, you can see that we have the fixed end moment at A, B, C, and D. Then again, we will carry out the so-called moment distribution method. And then you can see that we find all the member ends moment. And then from the member ends moment, actually, we can derive what is the horizontal force on the structures. And then if we apply the deflection, and then assume that there will be 100 kNm of the moment developed in the members, actually, when you add AX and the DX together, the force is equal to 56 kN. That means if it will create a so-called 100 kNm of the fixed end moment at the ends of the members, then actually the horizontal force will be equal to 56 kN. But instead, actually, we just need 0.92. So as you can see here, we do not need to use the whole member ends moment, but we will use a fraction of 0.92 divided by 56. And then 80 is the member ends moment when the force is equal to 56. So we just do it by proportion. We just have 56 as the denominator and then 0.92 as the numerator and then times 80, while 80 is the member ends moment. And then this is actually from the case 2. And then this is actually the moment from the case 1. So we just have the case 1 and then plus case 2, and then that's how we can get the member ends moment afterward. And then for each of the member ends, actually we do the same, and then we can find for the answer. But you just need to know about the way how to find for the moment for frame with sideway, okay? But don't worry about that because we won't put it in the examination. This one is too tedious to be an exam type questions, okay? But of course, you still need to know the way how to solve it, okay? Okay, so this is actually the end of the moment distribution. And then finally, I will go to the final chapter, which is actually, we call that is the approximate method for analysis. So this is the last chapter. We call that as the approximate analysis of statically indeterminate structures. So we will talk about the use of approximate methods for truss, and then for vertical loads on building frames, and then for portal frames and truss. And then finally, we will introduce two commonly used methods. One is portal method and the other one is cantilever method. And then we can use them to estimate the loads in our frame structures, okay? So here, why we need to use the so-called approximate method? Like you learned from the previous topics, basically we can solve for all the answer of within the structures by using equilibrium equations, or if we have more unknowns than the number of equilibrium equations, actually we need additional compatibility equations from the structures. Then, well, it can be a very tedious analysis and then time-consuming analysis actually. But actually, in many cases for engineers, we will have the so-called the initial design. The initial design basically are still in the preliminary stage. And then when we have the shape of the structures or the rough idea of the structures, actually we do not know what is the member size to be used. So at this stage, actually it is not necessary to have a full analysis of our structures. Instead, actually we can build a simpler model, and then the result is actually approximate, say for example, 80 to 70% of the accuracy, so that the engineer can guess or can estimate the size of the member based on the approximate analysis. So actually this is always for the engineers for determination of the size at the initial stage. So for this one, actually it is also important because this actually gives the engineers an alternative way to solve for the answer without going into too detailed analysis. Otherwise, actually we put too much time for preliminary design, which is actually not necessary. So actually, we will have some assumption to simplify our structures from our indeterminate structures to our determinate structures, so that we can find all the results by just equilibrium equations. Then we can estimate our size accordingly. This is actually the objective of using approximate analysis. But for here, for the truss, as you can see here, this is actually a truss with indeterminacy, because you can see that this is not a simple truss. You have quite many diagonals, okay? So if you count the number of unknowns and then count the number of equilibrium equations, you will find that actually it is an indeterminate truss with the degree of indeterminacy equal to 3. So we cannot just solve for all the answer by using the equilibrium equations. Then you can see that if we cut a free body at the location AB, actually you can see that there will be several member forces. You have F1, F2, and then you have FA, and then have FB. But if you treat the truss as a beam, then actually you will have a vertical shear at the truss panel. Then when your support reaction is equal to R1, then actually there should be a panel shear which is equal to R1 again, which is acting downward. So for here, actually we have free indeterminacy. I mean the degree of indeterminacy is equal to 3. So basically we need 3 assumptions in order to make the determinacy equal to 0. So for here, actually we can have 2 methods to adopt and then to reduce our degree of indeterminacy. The method 1 is that, if you still remember, we have 2 bracing, or we can call it as a diagonal. Now this diagonal basically is longer than our horizontal or vertical member because they are in the diagonal. And when structures actually it is long and slender, basically it is reasonable to assume that they cannot support the compression force, because you can think that it is long, and when it's subject to compression force, it is slender, and then it's easy to buckle. So the first method is that the compressive diagonal is assumed to be a zero force member. We can assume that the diagonal or the bracing member, which is having the compression force, it may actually carry zero force right there, because we assume that compression is to buckle. and then it carries no force. For the method 2, actually we can assume that, well, because actually one of the bracing actually is taking tension, while the other bracing actually is taking compression. You can go back and then take a look. When you have the force here, as I mentioned, when the force pointing away from the member, it is a tension. When the force pointing towards the member, it is compression. So for here, one of the diagonal will be in tension and then the other one will be in compression. And then, well, for the method 2 is that we can assume that actually they equally capable of supporting a tensile and compressive force. That means we assume that the force in the diagonal are the same. Both of them are equal to F. And then actually they are responsible to carry the panel shear together. So half of the shear is taken by the tension diagonal, and then half of the shear is taken by the compression diagonal. So this is the way how we can simplify our truss member. So for here, we will demonstrate to you how to simplify our indeterminate truss so that we can find the solution quickly. Right here, determine the forces in the member of the truss. The diagonal are to be designed to support both tensile and compressive forces. That means right here, diagonal like FB and then the AE, EC and then the BD, we assume that both of them carry the same load, and then actually they carry half of the shear. Okay, that means the force in AE and FB are the same, and then each of them actually responsible for carry half of the panel shear. So for here, you can see that we have the load 10 kN here, 20 kN here, and then for the support, we have 20 kN here and then 10 kN here. Okay. So for here, we will cut again the free body and then take a look. Well, you can see that this is actually the statically indeterminate structures with the second degree. And then we can assume that when we cut the free body diagram, we assume that both of the force within the diagonal is equal to F. And then actually, both of them are responsible for resisting the shear 10 kN here. So we are considering the summation of Fy going up is equal to 0. And then vertically, we have 20 kN, and then we have 10 kN going downward. And then right here, actually, we have F here. You can see that the slope is 3, 4, and 5. If we consider the vertical component, then it is actually 3 divided by 5 and then times F. So you can see that 3 divided by 5 and then times F is a vertical component. Of the panel of the diagonal force. So we assume that both the diagonal actually taking the shear. So we will times 2 here. So 2 times the vertical component of the diagonal force will be equal to the V. So we have 20 minus 10 and then minus this one is actually the V. And then which implies that the force within the diagonal is equal to 8.33 kN. Then the FFB is actually pointing away from the member, from the joint. So actually it is a tension force. So here, this one is a tension. Well, the one pointing towards the joint, actually this one is in compression. So you can see that in a very quick way, we have already found the values of forces in the diagonal. And after that, we will consider the equilibrium at different locations. Don't worry about that here. Again, we will use summation. And then this is the bracket. This is the bracket. Now, this is summation. This is implied. Now, don't worry about that because in your notes there will be no problem. Just in the PowerPoint, it shows some error here. Then, well, you just take the moment at the A. So you take moment here, and then you can find the values of FFE. Right here is simple. You have the values of 8.33. Actually, it is in the diagonal here. This is 8.33, and then you consider the horizontal component. So you divide it by 5 and then times 4. So here is the horizontal component. Horizontal component. Of the diagonal force. Okay, and then you have FFE times 3. So this is your FFE, and then you times the 3 is here. So you just the equilibrium and then take at the point A. Then you can find the values of FFE here. And afterward, you will use the summation of moment at F is equal to 0. So again, you will take the moment at this corner, and then you will have FAB as the unknown. And then you will use the horizontal component of FAE. So again, this is the horizontal component of the diagonal force. Then you can find FAB as well. So you can see that both FFE and FAB is equal to 6.67 kN. And afterward, you can use summation of Fy is equal to 0. So you can see that for here, FAF, and then the this one is FAF, is the member within this member. You also want to know what is the force within this vertical member. So you just take a look to, you consider the method of joint at the joint A, and then, well, you can write down the equilibrium equations for summation Fy is equal to 0. So you have FAF and then minus 8.33 divided by 5 and then times 3 becomes the vertical component of the diagonal force, and then minus 10. Then you can find FAF is equal to 15 kN in tension. Okay? So you can find all the member force here. And on the right-hand side, actually, you use the same way to find the diagonal force, and then you will find the vertical member force, FCD. So you can solve for the answer quickly. Now, otherwise, actually, you have the degree of indeterminacy equal to 2. Then actually, you need to use force method, and then to carry out some of the analysis, it will be more tedious. And then right now, you just make the assumption that the tension force and the compression force are the same, and then they take half of the shear for each one. Then you can solve for the answer. But of course, this one may not be correct because the diagonal force may not be the same. And then they may not taking half of the shear. Okay, this is just your assumption. Well, so for this one, we call it is approximate analysis because it is not the exact solution. It is just an approximation with assumption, okay? Okay, then after the truss, well, for the vertical loads on building frames, we can also use some approximation. Now, usually you will have a tall building like this. You can see that it is a frame structure. It has both girder and then the column. Now, the horizontal member, we call that this one is the girder. And then this is actually the column. And then this is the common arrangement of our beams and then the column. And then the vertical load is actually the loading applied vertically on the structure. And then before, if we need to analyze this kind of frame, it is a bit troublesome because actually it is a highly indeterminate frame. Then the degree of indeterminacy will be high, and it's very difficult to solve for the answer quickly. And then for here, actually, we will make some assumption and then make it to be determinant and then easy to solve. Okay. Now, first of all, we will introduce you a concept of points of inflection. What is points of inflection? It means that is the location of zero bending moment. With no bending moment. It is always happened when there is a fixed end. And I will show you quickly. But you can see that this is a typical beams or girder between the columns. Then, well, basically this one is indeterminate structures because you may assume that both are fixed end. Then you can think that here there will be 3 unknowns, and then on the other side there will be also 3 unknowns. And then you just have 3 equilibrium equations. So this is an indeterminate structures with the degree of indeterminacy equal to 3. However, actually we can take a look to the 2 structures here. The one on the left-hand side, we call that it is a beam with fixed support. Now, if it is with a fixed support, you can see that the deformation will be something like that. It will have no rotation at the ends, but actually it becomes like a simple support in the middle. So there is actually, we call that it is a point of zero bending moment. If I really draw the so-called the bending moment diagram, it will be something like that. This is actually the location without bending moment. Okay, this is the bending moment diagram. And then the differential shape will be something like this on the below. Then you can see that the location with zero bending moment is around 0.21 L. While L is the total length of the beam. Now, if the beam is actually purely supported by fixed support, then actually there will be a location around 0.21 L away from the fixed support. And at that location, the bending moment will be equal to 0. And then you can imagine that it is just like a hinge, because usually a hinge is without bending moment, okay? And then another extreme is that it is a simply supported beam. And then you can see that actually it will have rotation at the ends of the beam. And then there will be no distance from the support to have zero bending moment, okay? And then actually for the column like this, well, it is not a fixed support. This is not a fixed support. We can imagine that actually for the column, it will rotate a little bit. It can rotate a little bit. When it can rotate a bit, that means it has some flexibility. Then it is not purely fixed support. Then in this case, actually, it will have also have the point of inflections. That means the zero bending moment. But the location will not be 0.21 L because this one is for pure fixed support. Purely fixed support. Then it will be at the location of 0.21 L. And then for the case with the pin support, then it will be 0. So we take an average, we will use the distance of 0. This is for pin support. And purely fixed support, we just add them together and then divide by 2. And then we assume that the location of zero moment is equal to 0.1 L. So by assuming that, we can say that actually 0.1 L is just like a cantilever, while in the center of the beam, I mean after 0.21 L, actually this one becomes the simple support. And then on the side, actually, we can say that this is the cantilever. So for here, this is our way how to simplify our beam. Well, if we have a continuous beam while the beams or the girders are connecting to the columns, then we can simplify it as the cantilever, and then in the middle, it is actually a simply supported beam. So it is very similar to the beam like that. So our original beam is something like that, and then we can simplify it to this case in order to make it to be statically determinate. Because right on the left-hand side, the one actually is just a simply supported beam, and then it is actually a cantilever. So with that assumption, actually it is easy to find for the bending moment. And then for here, we can determine the moment at the joints E and then the joint C, caused by the member EF and then the CD. So for here, well, if we want to find the moment at the joint C caused by the loading at the span EF and then CD, will be very difficult before. And so right now we will use the simplification assumption. And then you can see that instead of using a beam, which is fixedly connected to the column, we will assume that it is consists of a simply supported beam, and then together with a cantilever beam. And then you can see that the length of the beam is 4 meters, and actually the total force applied in the center is 64 kN. Then actually you will have 32 kN on both sides of the ends. Then actually you can assume that there's 32 applied at the ends of the cantilever beam. And then at the same time, this one is actually a small cantilever. And then with 32 times the distance equal to 0.5. So you will have 32 times 0.5 as the moment due to these reactions. And then you will have also this 8 kN, which apply at on the top of the cantilever beam. And then times the distance 0.5, and then times the moment arm, which is equal to 0.25. So when you add them together, it will be equal to 18 kNm. So at the cantilever beam, it will be equal to 18 kNm at the ends. So that's why you can estimate quickly the member ends moment at the ends of the beam. So you will have 18 kNm here. And then to draw the bending moment diagram, actually you can draw for the simply supported beam. And actually this one is something like this. And then the cantilever, because you apply the load here, it will be something like this. And this is a cantilever, it will be something like this. So you just add them together. This is due to the simply supported one. And then on the side, actually, this is due to the cantilever. So this one actually is a very nice simplifications, which actually largely reduce the workload of the engineers. Okay, then we can go to the portal frames and then the truss. Now, portal frame is something like this. You can see that it is just like a C shape here. And then right now we are talking about the frame taking the horizontal force. So you can see that the force is applied to the frame horizontally. And then for the portal frame, it will be something like the portal frame in Chinese we mean that 好似龍門架係咪一個龍門架咁樣。Then if I apply the force on a portal frame, then assume that I have the pin support at the ends. Then basically you can see that there will be deformation on the frame, and then the bending moment will be something like that. It will be 0 here, will be 0 here, and then you can see that the bending moment will also be 0 in the around at the center of the beam. So as an approximation, actually we can, because the moment here is equal to 0, we can assume that there is a formation of a hinge at the center of the beam. This is the assumption or the simplification for the structures. And then at the same time, if you apply the force, around half of the load will go to the left-hand side and then half of the load will go to the right-hand side. So here for the pin supported column, we will assume that the horizontal shear force are equal. That means if it is the case, I have a pin support here. When I apply the load, I will assume that, saying that this is F, half will be here and half will be here. And then, as you can see before, the moment will be equal to 0 at the center of the girder. So we also assume that there will be a formation of a hinge at the center of the girder. So this is the assumption for the portal frame like this. And then if there's a portal frame, actually it is having the fixed end support. Later we will see it again. The bending moment actually will make it to be 0, not just in the in a girder. It will also appear in the center of the column. So actually, if you have the pins support at the ends of the column, it will be something like that. If you have the fixed support at the columns, then actually there will be formation of plastic hinge at the center of the or in the middle part of the member. And then once they have the formation of hinge, we assume that actually half of the load will be goes to the left-hand column, and then half of the load will be goes to the right-hand column. So this is the assumptions for the portal frame with fixed support or in a pin support. Okay, so with that assumptions, then we can take a look to structures actually with a frame. So for here, both A and then I are the pin, I mean the fixed support, and then we apply the load 40 kN laterally. Then as I mentioned, if we have fixed support at the ends, we can assume that there will be formation of the plastic, I mean with the hinge at the center. and then half of the load will be developed on the left-hand side, and then half of the load will be developed to the left-hand side. So for here, you can see that there will be assumed that there will be the development of the hinge in the center or in the middle of the column. Half of the load will be transmitted to the left-hand side, and then half of the load will be transmitted to the right-hand side. So you can see that you have action and reaction at the ends of the column. So you have 20 kN applied to the left-hand side, and on the other side, you have 20 kN to the right-hand side as well. So after that, you can apply the so-called the horizontal force equilibrium. So you will have 20 kN applied on the to the left-hand side, and then for the other column, you will have again 20 kN applied to the left-hand side. And then you can see that from the equilibrium point of view, 20 kN to the right-hand side, and then 20 kN to the left-hand side, and then times 3.5, you will create a moment of 70 kNm. So in order to resist this moment, the applied moment should be, at the fixed end should be equal to 70 kNm. So you can immediately estimate this moment is equal to 70 kNm because of when you consider the equilibrium of the column. And then actually you can with this one actually you can consider the summation of moment at the joint J. Then right here you can consider the equilibrium right here, and then you can consider the upper part. Then right here 40 is the force, and then you can apply rotation on this section, and then 40 times 5.5 we will create a clockwise moment. So it's here, and it is resisted by n times the distance. The distance here is equal to 8 meters. So you have n times 8. And afterward, you can calculate the vertical force N here. It is equal to 27.5 kN. So you can estimate the vertical force within the column. So summation Fy is equal to 0, so both N are the same. So you can find this is 27.5, then this one 40, and then the horizontal force is equal to 20. Then you will have again 3 internal force within the truss. And then, well, this one is simple. You just use the method of sections. You can use summation Fy is equal to 0, pointing upwards is equal to 0. And then summation of MB is equal to 0, summation of MD is equal to 0. Then you can imply that to find the force of FCD and FBH. Now this one is quite straightforward because after finding the force within the columns, actually just take moment at the location B and then the D, and then you use summation Fy is equal to 0. Then you can find the member force within the truss. Well, this one is very basic, and I think you can solve it by yourself. And then for the remaining members in the center, like the one here, the one here, and the one here, again, you can use method of join. To find for the answer. Okay, which implies this value. Now again, this one is basic, so you should be able to find for the remaining member forces. This is just the equilibrium based on the join method of join only. Okay. Okay, then we just apply the method not just on a portal frame, because portal frame is just have one girder and then the two columns. Okay, we can apply the assumption to our frame structures with multiple bay. But before you just have a portal. Portal means just 一個龍門架，係咪? But frame structures, actually, you can see here, it consists of many portals, okay? So as I mentioned, if there is a fixed support at the ends, then actually it will form plastic hinge. Not plastic hinge, it will form hinge in the center of the column. So for the portal method, actually we assume that the frame is made of a lot of portals. They are just stick together, okay? And then we assume that the shear will be taken the same for the portal. So if it is P here, we assume that this one is V. And then here, this is one portal and the other one portal here. Assume that this is V and then this is also V. This is V. So actually you can see that the two columns actually combine to one internal column. If we assume that a frame structure is consists of many portal frames together. So for internal columns, actually we assume that it is taking two V's, while for the exterior column, actually it is just taking one V. So if you have the portal like that, we will assume that it will form hinge at the center or in the middle of the structures. And then we assume that there will be one V here, and then you have two V here, and then again one V here. So totally we have four V's to resist the applied load. So here is our assumption. First of all, there will be a hinge placed in the center of the girder. This is our first assumption. The second assumption, there will be again a hinge, but it is at the center of the column. And then for the columns, actually, they will be taking the shear. For exterior column, we assume that it's just taking V. And then at the internal columns, they are taking two V's. So they are taking 2 times the shear as the exterior columns. Then actually, by doing that, actually we can reduce our highly indeterminate frame to a determinate structures. So I will illustrate by using this example. Now you can see that in the question, you are being asked to determine the reaction, the base of the columns of the frame. Then use the portal method of analysis. So for this one, first of all, we will assume that the hinge will form at the center of the columns and then the girder. So we assume that hinge will form here, form here, form here, form here, form here, form here, and form here. We assume that the hinge will be formed here. And then for each hinge, actually you can still, if you still remember, it can be decomposed and then it can become 2 reactions at the hinge. One is the axial force, the other one is the shear force. And then for here, actually, we assume that for the exterior force, exterior column, we assume that there will be V here. And then in the interior columns, there will be 2 V. And here there will be also 2 V's, and then here there will be V. Okay. So you can see that with this assumption, totally we have 6 V, because V plus 2 V plus 2 V plus V together, totally there will be 6 V's. And then apply on the top, there will be 6 Kn. So each V is equal to 1 Kn. So for here, we assume that there will be V here, there will be 2 V here, there will be 2 V here, and then V here. And then we assume that the summation of summation fx is equal to 0. And then 6 minus 6v is equal to 0. So you can see that v is equal to 1 kN. Now you can see that after that, if we decompose for each of our structure, so here is actually the axial force, then you just take a look to this one. Just take a look to this one. Then actually, there will be actually one horizontal reaction here. There will be one vertical reaction here. Then how many unknowns here? This one is M. So this is mx and this is my. So you have 1 unknown, 2 unknown, and 3 unknowns for this member. And actually you can write down 3 equilibrium equations. Summation fx is equal to 0. Summation fy is equal to 0. And then summation of moment is equal to 0. Then with these 3 equations, then you can solve for 3 unknowns. 3 equations, and then you can solve for 3 unknowns, okay? Now then you can solve for the answer. Now after that, of course, this is m. The other side is actually equal to n. So for this 3-body diagram, you also have nx and you have ny. And then you can see that after solving here, you have mx, you have my here. And then don't forget that you have jy here. This is unknown, but these two you have already solved. And then you have this one as unknown, this one is unknown, and this one is unknown. So again, for this body, you have again 3 unknowns. That means nx, ny, and then the jy. For the 2v, mx, and the my, you have already known. Then for these 3, the remaining 3, you don't know about that. It doesn't matter. Okay. You also have 3 equilibrium equations. So you use summation fx is equal to 0. Summation fy is equal to 0. And then summation of moment is equal to 0. And then you can again solve for the remaining 3 unknowns. And then for the next one, you can do that. And then for the final one, you can also do that. So you will consider 1 by 1. And then you can find for the answer. So right here, as I mentioned, you use summation of moment is equal to 0. You use summation fx is equal to 0, and then you use summation fy is equal to 0. Then you can find for mx and then my, and then you can find for iy. Because actually each part can write down 3 equilibrium equations, and then you can find for the answer. So you will find that part by part, and then afterward you can find all the axial force, and then you can find all the shear. Okay. After finding all the shear force, actually you just have the shear. You multiply with this distance, and then you can draw the bending moment diagram. Because this one just like a cantilever, you have a force, and then you can draw the bending moment diagram. Okay. You have the horizontal force, and then you apply this one just like a cantilever, then actually you can draw the bending moment diagram. And right here, you have applied the force, then you can draw the bending moment diagram. So you just have your shear force and then times the length of the member, then it becomes your bending moment. Okay. So immediately you can draw the shear, you can draw the bending moment diagram for your frame structures. Okay. And then the columns, actually you can apply at the same time, because you have the horizontal force, and then you will have one here, and then you have another one here, because they will be action and reaction pair. You have 2 here, and then you have 2 kN at the bottom. You have 2 here, and then you have 2 can at the bottom. You have 1 here, and then you have 1 can at the bottom, right? And then because actually the force are the same, and then there's a distance here, so you will create a counterclockwise moment. A clockwise moment. So in order to balance this moment at the member column's end, there will be 1.5 kNm at the bottom. Okay. Then you can also, from the upper member, you can find that the force is equal to 0.75 kN. So at the bottom, you have to have a reaction force equal to 0.75 kN to resist the applied load, which is equal to 0.75 kN. Okay. So this one is a very powerful method, and then has been adopted by many engineers when there's no computer. Then you can use this approximate method to calculate the wind force within your structures. Otherwise, if you have a very tall building and then the wind load applied to your building, before there's no computer, it is very difficult to estimate the values of the wind loads within your structures. And then this method actually has been used for years in order to estimate the wind loads and then for the design for the members under the wind load. Okay. The portal method, basically it is for relative low-rise building. Okay. And then there's another method, what we call as a cantilever method. Actually, this one is for taller building. Okay. Now we have a name as the cantilever. That means actually we will get the concept from a cantilever. Now you can think of actually a tall building. It is just like a cantilever. This is your tall building. And a tall building actually just like a cantilever, right? This is a tall building. And actually it is something like a cantilever beam, okay? Now for a cantilever beam, when you apply the loading laterally at the ends of the beams, then actually it will create compression force on one side, and then it will create tension force on the other side. And then here is the centroid. Of the beam. That means it is the neutral axis. It is the location without any bending stress of the cantilever beam. So actually at this location, there will be no stress. While on the upper part of the beam, there will be compressive stress, and then in the lower part of the beam, there will be the tensile stress. So actually, as I mentioned, a tall building, when it is subject to the wind load or earthquake load, actually it is similar to a cantilever beam. So actually there will be also a compressive force into the column, and then there will be tensile force in the columns. And then we just use this similarity and then apply to the so-called the tall building. And then you can see that actually the force or the stress within the structures is in a linear sense. So the far further away from the neutral axis, actually the stress will be larger. And then it will be in a linear manner, okay? The further away from the neutral axis actually is the larger of the bending stress within the elements. So you can see that actually we can use this similarity. We apply the lateral load to a tall building, and then you can see that one side of the column is actually in compression, and the other side actually is in tension. So for here, actually this is in compressive stress, while the other side is in tensile stress. So you can see that when the column or when the building is under the lateral load, actually the columns are subjected to axial force. And then depends on the location of the column, they can be subjected to tension force or subjected to compression force. And then of course the stress within the column will be depends on the distance from the neutral axis or from the centroid of the column area. The farther away from the centroid actually will be larger of the axial load. So for here, this method, we will use this concept for analysis. And then for the cantilever method, again, we will assume that there will be a hinge developed in the center of a girder. And that hinge is developed at the center of the column. And then we will also assume that the axial stress in the column is proportional to its distance from the centroid of the cross-sectional area of the column. And then depends on the location of the centroid, actually the axial load will be different. So right here, we will have two examples and then to illustrate to you how to use the so-called cantilever method. And then for the first one, actually the columns area are equal. That means the centroid of the columns of this neutral axis is the center of the structures. So for here, we have 30 kN applied to joint C. And then we have 15 kN applied to joint B. As I mentioned, we will have the so-called hinge formed at the center of the columns and then at the center of the beam. And then as the centroid of the columns is in the center, so both of the force within the columns will be the same. So HY is in tension while KY is in the compression. But as the centroid is the center, so HY will be equal to KY. Then how to find HY and KY? It is simple. You just take moment right here, and then you have 30 divided by 2, and then you have KY times 6. Then you can find the values of KY. You just use moment equilibrium. Or in our notes, we will take the moment about the centroid. Because HY is equal to KY, then you can find the values of HY and KY accordingly. So you can see the summation of moment here. We take moment at the location of the centroid. So the applied load 30 and then times the distance is 2. While HY with a distance of 3 meters from the centroid and KY with a distance 3 meters from the centroid as well. And then we know that HY is equal to KY, so we can get the values of HY and KY and then equal to 10 kN. So this one is quite straightforward. And then afterward, you can apply the same one at the columns in the lower story. So again, GY is equal to LY, and then you can take moment about the centroid. And then you can find the value is equal to 35 kN. And then again, once you get the axial force, once you get the values of the axial force, once these two are fine, then you can find the free body diagram for this one first, because there will be two unknown here. Then you can write down three equilibrium equations because you have summation Fx is equal to 0, summation Fy is equal to 0, and then summation of moment is equal to 0. Then you can find the member end forces. After finding this one, you can find the next one. And do it one by one and then so on. And then you can find for all the member ends reactions. So that's why you can find for IY and IX, and then you can find for HX. So you can find it one by one. and then you can find the axial force and the shear forces. It is not difficult, actually, I can say, for this method, but it is quite time consuming. So you have to do it quickly, otherwise you may not have enough time. And then this one, actually, you can see that it is actually the columns with the different area. So again, we can use the same concept, but for here, we first of all need to find out where is the location of the column. Once you find the location of the center of the column, then you can go ahead. So for here, we have 2650 first for the first column, and then 5000 for the next, and then 3750 for the next one, and then 6250 for the next one. And then we can assume that our reference axis is at the first column. So the location of the first column is 0. So the location of the second column is 6 meters. And then the location of the first column is 10.5 meters. And then the last column is 18 meters away from the reference. To find the centroid, actually it is not difficult. You just use the column area times the distance and add them together and then divide by the total column area. Then you can find for this location of the centroid. So for this one, you just use the 0 and then the first column area, and then 6 is the location for the first column, and then the first column area, and then second column location, and then second column area, and then so on. You just add them together. And then for the value, you will divide by the total column area. And then you can find the centroid is equal to 8.559 meters. So for here, you can find that it is equal to 8.559. You can say that it is 6.56. So you can see that on the left-hand side is 6.56, and on the right-hand side, the length is equal to 9.44. So if you cut the three-body diagram, you can see that actually the stress is something like that. This is the stress within the column, sigma L. This is the stress. That means this is the location L, M, N, and O. Okay. And this is the stress within the column M. This is the stress within the column N, and the stress within the sigma naught. Okay. Now actually, this one is a straight line, because we assume that it is the plane section remain plane. So we just use this straight line and then we put it here. Actually, it is on the same straight line, okay? So these two are the similar triangle. Okay, so we can put sigma M, sigma N, sigma O, and then sigma L together by using the so-called similar triangle. So by considering this triangle, you have sigma M and then sigma L here, and then you have 2.56 and then 8.56 here. So this relationship is actually written by considering similar triangle. And then you can see that sigma M is actually equal to the force within the column M, and then divided by the area. So this one is actually the sigma M. And then this one is actually the Ly is the force within the location L, and then divided by the area. So this one is actually the sigma L. So you can relate my with ly. And then for the second one, you can see that sigma n can be related to the sigma L. So sigma L here, sigma n here. So again, you can use similar triangle. You can use this distance 1.94, and then you can use 8.56 because they are actually again on the same line, same straight line. So they are again a similar triangle. Sorry. So here again, this one is the force within the location n, and then divided by the area. So this one is sigma n, and then this one is sigma L. So again, you can relate ny to ly. And finally, this one is also a similar triangle. You use this distance because this is sigma O, and then related to sigma L, then use 8.56. Then this one is actually the sigma O, and this one is actually just the sigma L. And then again, you can relate OY with LY, okay? So with this one, actually, you can find out the values of LY because you take the moment at the location at the here. At the centroid here. So you have 36 times 1.8. And then in clockwise, that means it is negative. And then you have Ly times 8.56 because you take moment about the centroid of the column. So it is Ly times 8.56. And then the next one is My times 2.56. And the next one is this one times 1.94. And the final one is 1.103 times 9.44. Then once you solve for the values of Ly, because before you have already replaced Ly with My, Ly with Ny, and Ly with Oy, then you can find for the values of all the column forces. And then you use the same way for the columns below. So you have EY, FY, GY, and HY. You just do it in the same way. After finding the column axial force, again, you will consider each part of the frame. Using 3 equilibrium equation for each part. Okay? And then you can find for all the reaction force at the member ends. Okay? This one I think is not difficult, but you have to practice so that you can know how to do that. Otherwise, if you don't practice, then you don't know how to do that. Okay, so this is the end of this chapter. So I can say that I finished all the chapters within this semester, okay? So next week we will still have the tutorial section for this chapter, and then we will have some revision for the important points. 好啦，咁要講嘅部分咧，呢個 semester 嘅部分咧已經係完結啦，係得咁多啦。咁當然啦，頭先都講份功課會褪到下個禮拜一啦，因為大家可能都要多少少時間啦。咁另外咧個 lab 嗰度咧，因為我唔知你哋嗰啲 group member，咁唔該你哋 send 翻個 group 嘅名俾我啦，咁我幫你擺翻上 Moodle 啦。同埋咧，下個禮拜咧就同各位講一講啲重點啦。咁大家咧都要 practice 下嘅，即係要溫下書啦嚇。咁如果你唔做下咧，你到時好難搞㗎嚇。咁講咗重點之後咧，大家都要翻去做多啲，得唔得？咁有冇咩問題想問？
考試咩
嘢話？
係咪一定合格㗎？定係 over all 合格得㗎？
我哋就冇需要功課同考試都合格嘅，總言之你 O4 夠40分就合格啦。即係考試你唔合格，但係你功課答夠合格都可以，得唔得？
好啊，唔該晒。
OK， 盡量啦嚇，做得幾多得幾多啦，咁盡量攞分嘅啫都係。如果你真係有困難嘅，就翻嚟做下咯。咁你想約時間揾我傾下都得嘅，因為你其實要做多少少嘅。如果你完全唔做，其實係難搞啲嘅。咁如果你真係需要嘅，你想翻嚟傾下得嘅，你咪約我咯。好嘛？好，有冇問題？仲有冇嘢想問？OK， 如果冇咧，我哋今晚到呢度啦。咁啊有嘢喺 WhatsApp 揾我啦，係嘛？